Hello, we are Project Pinot. My name is Bessie Steinberg. My teammates' names are John Kolnik, Jingwen, Kris, and Lucy Yan. Our assignment over the last year has been to create a smart irrigation system for a home garden for our customer, Isabel, Pisano. So far, all of our things are fully functional. The only thing left to do is install it, which we haven't done because then we wouldn't have a product to show you today. It wasn't part of our project. We got a lot of feedback that users would probably want different areas of their garden watered differently. Let's say you have like one section of the garden is full of flowers that really need a lot of water, and then you have a bunch of cactuses over here. Like clearly they need very different amounts of water. So we responded to this need by having different moisture sensors throughout the garden that collect data on different zones of the garden, and then solenoid valves that will control flow of water to that specific zone and can be opened and closed independently. The basic flow of our system is that rainwater flows off the roof and then is collected in the rain barrel. There is a Raspberry Pi installed next to the rain barrel that decides if the pump is on or off, and if the pump is on, it decides which of the solenoid valves should be opened. The moisture sensors in the garden collect data and then transmit that data wirelessly to the Raspberry Pi. It's important that those moisture sensors are housed within a waterproof container that is also sturdy enough that it can hold up to wind or like a neighborhood cat maybe. And we also were concerned that clunky electronics would look really bad in a garden, so we decided to house this inside of a garden gnome like the one pictured here. The last component of our project is a web application where the user can view data that we've been collecting on their garden and also change the watering parameters. And now Lucy's going to talk about hardware.
Hi, I'm Lucy. I'm going to give you a brief overview of hardware. So in the picture you can see we have 3 solenoid valves. These are attached directly to the Raspberry Pi and controlled by the Pi. There's an XB and an antenna. An XB is a radio module, and we can receive soil moisture data from the garden wirelessly. And also housed inside of the rain barrel is a water level sensor directly connected to the Pi so that at all times we know how much water is left inside of the rain barrel. One thing that's not pictured on here is the relay, which is what the Pi uses to control power on and off to the pump. Now for the gnome side, housed inside of the gnomes are rechargeable batteries. You can screw off the gnome head. Not a joke, you can take the head off. It's made out of an old almond butter jar because some people have peanut allergies. I have peanut allergies. We use resin epoxy to make the outside gnome. To make the outside of the gnome, it dries overnight into a solid, rigid structure that is waterproof. Then we paint it over it with acrylic paint and put over a UV gloss so that we waterproof it one more step and also preserves the aesthetics of the gnome. Here's another picture. Inside is the PCB, which I'll talk about a little bit later. Now I'd like to invite my fellow friends and teammates to talk about their contributions to the project.
So the first thing I had to do was research in Selective Pump for our project. I chose the Ponix Pump 800. I also had to monitor water level in the rain barrel. There's several reasons for this. Firstly, the user wanted to collect data on that. Secondly, our pump is submersible and it's dangerous to run a submersible pump with no water. Thirdly, if there wasn't enough water to water the garden, we wanted to make sure that we could alert the user via text message so that their plants didn't get sick. The sensor that I chose is essentially a variable resistor that changes resistance based off of the amount of water it's submerged in. There is no onboard analog to digital converter on the Raspberry Pi, so in order to measure this, we had to use an external ADC and communicate with it using the SPI protocol.
So my role is to design a feedback system that allows the user to monitor the moisture level in the garden and help make watering decisions. A moisture sensor is used. It's attached to the bottom of the gnome. The tube-hole will be stuck out that goes into the soil. After successfully collected data, it will output those data in analog form to the XB. The XB gets the data converted into a digital form, used built-in ADC converter, and transmitted to the Raspberry Pi. The system will sample the moisture data once an hour for a couple seconds, and this is done by using a microcontroller that control a power circuit that's connect to the sensor and also control the slip pin on the XB.
Okay, so my part of the project was to create a web app that lets the user control and keep track of the system. So it's built with a combination of HTML, CSS, and JavaScript with a parse database as the backend. So you can see here that the website has a few functions. On the left, you can see an animation that the user is dragging the dial to set a desired moisture level for that zone. And we have other things like you can keep track of how much water is in your barrel currently, as well as further customize the system with the zip code. And what that does is it lets your system know where you are and make better watering predictions based on the weather forecast. And then finally, if you don't like our smart watering algorithm and you just want to override it, you can actually put in your own schedule for the week. And we mentioned zones earlier, so I just wanted to show you what the solenoid valves look like. So when that gets 9 volts, it opens up and lets the water through, as you can see from the bottom there. Kris is going to talk a little more about that.
So my part of this project is to write software on the Raspberry Pi, which is our control system. So how does this system actually work? So our system provides 2 different modes, smart watering mode and manual mode. For smart watering mode, our system collects the soil moisture data constantly and saves the data to the local database on the Pi. And the system also collects the moisture setting from the cloud database, which can be altered by the users on the web app. Every once in a while, the system checks if the current moisture level in the ground is lower than the setting for individual zones. And if it happens, our system turns on the pump and opens up the solenoid valves for the individual zones. But before that actually happens, the system checks the water level first, see if it's below the threshold, or for the current location, if it's raining, based on the data provided by Forecast.io API. And if either case happens, the system won't turn on the pump. As for the manual mode, when the user set the weekly watering schedule, our system checks if the current time is the scheduled time of the day, and if it is, the system turns on the pump and opens up all the solenoid valves for the duration as the user desires.
My main responsibility for the project was to make sure that the gnomes worked. The circuits inside I designed and tested to support the soil moisture sensor. The MSP430 uses an NPN as a switch to turn power on and off to the soil moisture sensor so that it's not on 24/7, because we don't need to know how moist the soil is at 2 a.m. We also put the XP to sleep so that it draws a very limited amount of current while it's in sleep mode, and this allows us to use 2,000 milliamp hour batteries to operate for at least a month. This is a very safe factor. Like, in reality, it'll probably last 2 to 3 months, but just to be safe, we're saying it's 1 month. Oh, that's the PCB I designed and manufactured. It turned out great. It works. Now I'd like to show you a video of our project. Maybe.
Here we have an example of setting the desired moisture level above what the current garden moisture is. As you can see on the left, after saving this new setting on 2 of the zones, the zone relay will activate these 2 zones, indicated by LEDs 1 and 2. After watering for the proper amount of time, we fast forward to when the zones have reached the desired moisture level. At this time, the system deactivates the zone solenoids and the pump. To demonstrate the alternate method of watering, here's a quick example of how we set up a manual schedule.
So senior design has allowed us to apply our engineering skills to a real world problem. This has been an amazing project which has touched upon all aspects of our engineering education. We're really excited that all our components of our project are working, and we're looking forward to installing our system soon after ECE Day.
Special thanks to Professor Pisano for his wisdom and guidance, and Professor Kia for staying late in the lab and helping us out. And thanks to our friends in the Epic Lab and the Imagineering Lab for the help on the mechanical components of our project. And lastly, a special thanks to all of our friends and peers who cried and laughed with us in the Senior Design Lab during this process. Best of luck, everyone. Here are pictures of 2 of our domes. If you want to come see the other ones, they're on the other they're at our table. If you have any questions, we'd love to answer them.
Did you guys notice any sort of delay between adding water to the soil and actually reading it with your sensors?
So we haven't installed the drip lines yet, so it's hard to really see how the water's going to dissipate over it, but as far as in the lab, there really wasn't much of a delay.
Have you guys built any functionality in the software to account for that if it does actually do the case?
No, we imagine there's going to be a little bit of tweaking once we
Yeah.
install.
It is,
Yes.
You mentioned the battery will last a couple of months, but is there the low battery notification system?
Okay, so that's a very good question. Oh, we have 3 gnomes in our garden, and each is charged by 4 1.5 AA size batteries. And they're 2,000 milliamp hour, and according to our power calculations, 1 month is a crazy safe limit. So the idea is, for the first time you install it after a month, you pop open the head. There is an additional circuit I attached to about a week, 2 weeks ago, so it's kind of last minute. It's not that pretty, that's why I didn't put it in the presentation, but basically it's an LED and you switch the power circuit over to the LED, and depending on the voltage of your batteries, it's either super bright or super dim. It's designed so that at 3.3 volts, which is the bare minimum you need to have to drive our circuit, the LED is very, very dim to off. So if the light is dim, it means you need to charge your batteries.
And what does this cost?
Per
Since
gnome?
per gnome or the whole system?
Yeah, well, whole system and then per gnome.
we give you the breakdown roughly. I mean, we purchased duplicate parts, etc. But the XP runs about $30, the antenna is like $5, the moisture sensor is like $5. So I would say the gnome comes into under $50. And then if you don't have a pump already, that can range anywhere from
That's from like $40 to $100, depending on
how powerful.
how powerful you need it.
And
And
the Pi is 35. The solenoid valves are each 10. So I'd say the base station is also less than 50, maybe less than 75, and that's about it. So.
Did you guys think about incorporating solar power to recharge? Or?
yeah, we did.
That was one of the first power systems we thought of, because it'd be really nice. You could just set it in the garden and forget about it. But the thing is, gardens, the particular garden we were working with had a lot of big trees in it, and it was pretty shady. And Massachusetts doesn't get a lot of sunshine, especially not in Boston. It depends on the weather. I mean, who knows? It might snow in April. So we did look into it, and we also considered wind energy, but since if we made the wind turbines, they'd be really close to the ground where you don't get a lot of wind. So.
All right, thank you.